Hello, geometry students. In today's lesson, we introduce the concept of probability. And it's actually a very simple concept because probability is what you want over total possibility. It's as simple as that. It will always be a fraction with the number of things you want on the top and the number of things you're choosing from on the bottom. I'll usually write it as a fraction, but sometimes I'll go for a decimal or even a percentage. So look here, we have a standard 52 card deck. Some of you may not be familiar with it. That's why I have a picture of it here. I'm going to draw a single card from this deck at random, and I want to find the probability of the following. Find the probability of drawing a heart. Well, probability is simple. It's the number of things you want over the total number of things that you're drawing from. The total number of cards in this deck is 52. How many of them are hearts? There they are. There's a total of 13. So the probability of drawing a heart from a deck of cards is 13 over 52. 13 over 52 is a perfectly acceptable answer. It simplifies down to 1/4 or 0.25. It's also 25%. You need to be aware of how to do all of those, but generally I will stick with the fraction. Well, you reach in, put it back in, you shuffle it up. What's the probability of pulling out an ace? Well, there are 52 cards that I'm choosing from. How many of them are aces? 1, 2, 3, 4. 4 aces. So you have a 1 in 13 chance of getting an ace. I don't remember what that decimal is. 0.7. 0.77. Or if you preferred a percentage, 7.7% of the time, if you draw a card from a deck at random, it will be an ace. How about this one? We're talking about an ace and a heart. At the same time, I'm only drawing one card, and I want that card to be both a heart and an ace. Well, that's another way of saying the ace of hearts, and there's only one of them. So any one particular card, there's only a 1 in 52 chance. We think of the ace of hearts as being special, but they're all special. And the decimal for that is 0.19. So right at 2%, you have a 2% chance of drawing any specific card. It's always the number of things you want over the total possibility. That's all there is to probability. The key, of course, is figuring those two numbers out. All right, now we have a deck of 6 cards. A single card is chosen from the 6 Spanish playing cards over here. Find the probabilities. Well, first of all, there are 6 cards. So anything I draw is out of 6. That number doesn't change unless I tell you something in advance. That's coming up in another lesson. I want the probability of an even number, so just count the numbers that are even. There's a 10. That's 1, 2, 3, 4. 4 of them have even numbers. Don't look at the number 4. Just think that there are 4 with even numbers. That, of course, simplifies down to 2 over 3, or the decimal 0.6 repeating. How about a card with a human figure? Well, from among 6 cards, 1, 2, 3 of them have a human figure. That's 50%. Half of them. How about this? This is unusual because it says a prime number, but specifically it has that little squiggle in the front. That squiggle in the front means not. So I want this to not be a prime number. So what I'm going to do is, there are 2 ways of doing it. Just go through and count the ones that are not prime numbers. 10 is not prime, 10 is not prime, 4 is not prime, 4 is not prime. 1 and 11 are. So 1, 2, 3, 4. There are 4 of them. That's the answer, 4 out of 6. But generally, in order to do a not, you should generally subtract from 1 all the ones that are prime numbers. So 1 and 11, there are 2. But that gets me back to the 4 over 6, which is 2 over 3. There's some question about whether 1 is prime, but we're going to consider it that way here. Look at number 3. Number 3, try it again. The spinner. You spin this spinner, it's going to land on a number at random. The spinner is 1 through 12. You spin a spinner with 12 numbers, 1 through 12. Find the probabilities. In this one, I'm looking for the number 5. There's only one 5 on this. Don't be confused with the digit 5. It's not like it's going to be 5 out of 12. This is what people will do. That's wrong. It's not 5 out of 12. There's only one 5. So the answer is 1 out of 12. I'm going to leave it as 1 over 12. You can get the decimal if you want. So among 12 choices, how many of them are even? Well, 1, 2, 3, 4, 5, 6. 1/2, that's generally the case. All right, how about a number less than 5? Among 12 things, how many of them are less than 5? Less than 5 does not include 5. It must be less than 5. So I'm only looking at 1, 2, 3, 4. The number 1, number 2, number 3, and number 4. There are 4 of them. You have a 1/3 chance. And how about this last one? On the spinner, what's the probability that you get a number greater than 12? In one spin, how many numbers are greater than 12? Well, 0. Out of a total of 12, there's a 0% chance that you're going to win. I say you're going to win $1 million if you get a number greater than 12. I can say that because it's not going to happen. How about Venn diagrams? A Venn diagram, of course, if you look at the Venn diagram, this number here, the 17, represents 17 individuals located in this circle. The number 5 means that there are, say, 1, 2, 3, 4, 5 people standing in that section. These people standing in the middle of the eye here, they're also in this group here. They're not included in the 17. They're not included in the 11. So, 2. If you look at this, you count all the people standing in this circle, the Algebra 2 circle. It's these 11 plus those 5 for a total of 16. That's how a Venn diagram works. I don't want to put the numbers in. I don't want to put the dots in because I don't want to have to count them up. But the 17 means there are 17 people standing in just that portion. There's another 5 standing in this portion for a total of 22 that are standing in the geometry circle. So with that in mind, I'm going to choose a student at random, and I want to find the probability that that student is in geometry. Well, I already said there are a total of 22 in the geometry circle. But I have to add up the total to find the total number. There's 17 plus 5 plus 11 plus this 3 who aren't in either for the total of 36. So out of 36 people, 22 of them have geometry. That's the answer. It's what you want. I want someone in geometry. Out of a total of 22, that is about 6%. Same thing for Algebra 2. Among 36 people, how many of them are in the Algebra 2 circle? Well, it's these 11 plus those 5 for a total of 16. And that is 0.4, repeating, about 4%. Both means that you are going to be in both the geometry circle and the Algebra 2 circle. It's these people in here that are standing. This person here is in the geometry circle. That person is also in the Algebra 2 circle. That's what I mean when I say both. There are a total of 5 of them. How about neither? That means you're not standing in either circle. Out of 36 people, only 3 of them are not standing in either circle. That's what the 3 outside represents. Whoops. 0.83. About 8%. Here we see this little squiggle again. That little squiggle, of course, means not. I want someone who is not in Algebra 2. That means everybody who is not in that circle. If you see a knot like that, it's customary to do 1 minus. So I'm going to say 1 minus the probability that I've already found that you were in Algebra 2. So 1 minus 16 out of 36. That's 5/9. Or the decimal. Now, there's another way of doing it. You could actually count up all the people that are not in this circle. It's the 17, 18, 19, 20. So it's 20. In fact, I think I'm going to write that. It's these 17 and those 3 or those 20 that are not. And then finally, we got one more notation, and that's this or. Or means that you can be in either geometry or algebra. If you ever see an or, you're going to add all the people in geometry, 17, plus all the people that are in algebra. Well, I'm doing this wrong. This is actually a different concept. Basically, just add all these 3 numbers. 17 are in geometry alone, 5 are in both, and 11 are in just algebra 2. You could also see that this is the complement, or excuse me, the not of the neither, so I could just subtract. But I've already added it. And I get, oh, it's 11/12. About 91, 92%. All right, switching gears, look at sample space. A sample space is simple. It's just a list of all possible outcomes. We've already seen it when I showed you the deck of cards. It was a list of all possible outcomes. So suppose you flip a coin. What are the possible outcomes? You could either get head or you could get tails. What if you have a spinner with 4 different colors? Well, it can either land on red, yellow, green, or blue. It's a list, usually a set notation. Those are the possible outcomes. I got a bag full of marbles. Some of them are blue and some of them are red. You can either pull out a blue marble or you can pull out a red marble. If you want to be more specific about this sample space, you could actually list the number of blues. You could do something like this. That might be a little more helpful. In this case, I'm just looking for write the sample space. A new card is available in either white, black, red, gray, or blue. So it's either white, black, red, gray, or blue. That's the sample space. A spinner numbered 1 through 5. The sample space is, you can land on a 1, a 2, a 3, a 4, or a 5. That's just a list of the things that are in